Hi there, let me show you a few compilations I made on chemistry experiments. Don't get this wet, but I did.
Check it out. This is a kilo of gallium metal.
Gallium is a liquid at just barely over room temperature.
Unlike mercury, gallium has low toxicity, so it's much safer for experimenting around with. Gallium is also much stickier than mercury, which means it's useful for making DIY mirrors by simply painting it on glass. Even the liquid itself makes a good mirror, and it easily reflects this laser beam to light a match. Pretty cool, right?
I'll be popping balloons with orange peels. Alright, so all you're gonna need is a balloon and an orange peel. Alright, blow her up. Now, get someone to tie it. Okay, you may be wondering, how can this pop? So basically, right inside this orange peel is a compound called limonene, which is a hydrocarbon. So basically it's made up of hydrogens and carbons. Then, because limonene is a hydrocarbon, and hydrocarbons are nonpolar, one would expect that limonene is in itself nonpolar. Like limonene, the rubber in balloons is also a hydrocarbon, so it's also nonpolar. So it's well known by chemists that nonpolar substances dissolve other nonpolar substances really well. Let's see this in action.
And fire, never a winning combination unless you have the secret ingredient, water. Water is amazing. Watch this. I'm going to do it again with a clear balloon. The water goes into the balloon like this, and then we're going to blow it up. What's amazing about this is you think the balloon's going to pop, but actually the water draws the heat away from the latex, and we hope that it doesn't burn. So watch, we light the candle once again, and now look at this. The heat, get ready, look at this. The heat now is being pulled away from the latex by the water. Through convection now, it gets hot, rises up to the top, it's cooler there. It keeps doing this until it finally boils. How long will that take? I don't know. You're going to figure that out.
Water, and cinnamon. Yet, your finger stays dry after you dip it in. How is that possible? Science.
Chem class rules here. Today we're going to show you the making of the chemical traffic light. Now for this reaction you really only need 4 ingredients: water and indigo carmine that I just added to the flask there. Indigo carmine is a blue food dye and it's also an acid-base indicator. Give that a little swirl to get it nice and mixed up. The next ingredient is sodium hydroxide. Sodium hydroxide is also called lye, and it's in most drain cleaners. We'll give it another swirl here to get it nice and mixed, and it's also going to start to show us a little green color. The next thing we're going to add to our flask is going to be some sugar. It has to be glucose or dextrose or reducing sugar. It can't just be regular table sugar. This creates what's known as a reversible oxidation reduction reaction. When we shake the solution up, we're adding oxygen to it, which oxidizes the indigo carmine from yellow to red to green. And then, as the solution sits, the sugar reduces the indigo carmine from green to red to yellow. That's the reason for the color change. So there we've drawn out the different stages of the molecule for you. And there we have our final solution. Starts out yellow, give it a little shake, incorporates some oxygen, oxidizes that indigo carmine up to red. The sugar reduces it back to yellow. If we give it a little more vigorous shake, we go through red and get to green. And as it sits, the sugar reduces it from green down to red. And then if we let it sit, it will come back to yellow. Here we are pouring it out. You see the yellow in the flask and the green in the large beaker. But once we stop adding oxygen, it goes right back to red and then to yellow. Thanks for watching, guys.
crazy thing online and I wanted to try it out for myself. It said if you put a battery in pure water, the water molecule is electronically neutral and not much happens. But if you mix some salt in the water, things are different. The salt dissolves in the water to leave behind positively charged sodium ions that migrate towards the negative tank and negative.
You can do this at home. Cold water in the bottom. That's what the blue is. Hot water in the top. The card separates them. Watch what happens when I pull like this. Look at that. Cold there, hot there. There you go. Now try this. Same thing, but this time we'll put the hot on the bottom and the cold on the top. Watch what's going to happen. It's going to be your job to explain what's going on. Look at this. Look at this. Now come back over here. No mixing whatsoever. Hot on the top, cold on the bottom. But when you come over here, look at the convection currents. Cold on the top, hot on the bottom. That's what the yellow is. And all of a sudden we start to get green. Why does this work? And what does this have to do with temperature inversion?
Know these chemical reactions. Pour the milk into the Coke. Cover and shake evenly. You'll see a lot of sediment. This is protein denaturation. Soak an egg in white vinegar all night. Get an egg that has no shell and elasticity.
It's cloud in a bottle. Check it out. It's so easy to do. You need high pressure, you need condensation, and then release the pressure instantly. Here's the first thing you're going to need. A bicycle foot pump. It's perfect because you can control the air going into it. Second thing is that valve stem right there. That's a tire valve stem, a little stopper. It just fits perfectly into the bottle. And the last thing, rubbing alcohol. Now normally water would be used, but it doesn't evaporate fast enough. So just a little bit of that rubbing alcohol inside, that'll give us the evaporation that we need. Try different strengths to see which kind of cloud you get, but watch this. Pump it back up again. You're going to feel the bottle getting warmer. The pressure's building inside. When it feels good, release it quickly. 3, 2, 1. That's your cloud in a bottle. Original boo bubble activity, but you don't have any dry ice. Don't worry at all. All you need is a humidifier. That's what I'm using here. So I took a hose, hooked it onto the humidifier. Now we've got vapor. Now it's not super strong, but in terms of pressure, but it's just enough to be able to create the bubble. The bubble won't pop on your hand because there's no oil or dirt that's there. It'll stay on the towel every once in a while, and you can do the original boo bubble activity without using the dry ice. All you need is one tiny little crystal. That's it. Look at that crystallization happening. Have you ever seen those hand warmers that you click the little tab and it starts to crystallize? It warms up. Look at that. That is the heat of crystallization. It's an exothermic reaction. It's because this chemical right here called sodium acetate trihydrate went from a liquid into a solid. It's a supersaturated solution. So you take the crystals with a little bit of water and you turn it into a liquid like this. It's a supersaturated solution. When it cools, all it needs is a single crystal to go. And that's what we're going to do here. So one more crystal will start the crystallization and it will turn from a liquid into a solid. Watch. That's it. Look at this, and there it goes. That entire thing starts to grow. Look at how amazing that is and how beautiful that is. Within seconds, the whole thing turns from a liquid into a solid. You turn it upside down and nothing comes out, and it heats up at the same time. It's the secret to the coolest hand warmers you could ever find. Just look at that.
Candle completely underwater, but it's not going to go out. Watch. This is possible thanks to air. The air in the cup takes up space and protects the candle from getting wet. However, if you hold it underwater for too long, it loses its oxygen supply and burns out. Try it for yourself and follow for more science videos.